Throughout human history, the universe has always been a subject that offers far more questions than answers. For thousands of years, people have looked up at the night sky, asking profound questions about the origin, fate, and true nature of the world around them. By the 20th century, scientists believed they had built a solid foundation for understanding the cosmos, with the Big Bang theory, the standard model of physics, and concepts such as dark energy and dark matter. But in recent years, a series of new discoveries has emerged, and each one has struck like a heavy blow against what we once thought was certain. It was against this backdrop that the James Webb Space Telescope delivered a set of startling findings, results so unexpected that they have forced the scientific community to re-examine nearly every assumption about the origin and evolution of the universe. These new data don't simply add detail to the larger picture. They make that picture more complex, more intricate, and more mysterious than ever before. More and more researchers are beginning to believe that we are standing at a genuine turning point, a moment that could change humanity's entire understanding of how the universe forms and moves. Dr. Andrei Koutau, a researcher at Lawrence Berkeley National Laboratory in California, put it this way during an interview: "We've always let the universe tell its own story, and perhaps now it's telling us that it's far more complicated than anything we've ever imagined." His words resonated deeply within the scientific community, not only because they acknowledged human humility in the face of nature, but also because they reflected a growing concern that the old theories may soon need to be replaced or rebuilt from the ground up. In truth, every time humanity pushes the boundaries of its understanding, the universe seems to respond with new riddles. Advances in astronomical technology, especially modern space telescopes like James Webb, have allowed us to peer further back in time than ever before, observing tens of thousands of galaxies from the universe's earliest days. Yet instead of reinforcing our current cosmological models, these discoveries are producing more and more contradictions, forcing scientists to ask, could we be on the brink of some vast truth that we cannot yet comprehend? This uncertainty is no longer confined to laboratories or academic conferences. It has spread across the globe, to science enthusiasts, to anyone intrigued by the mysteries of space. Questions like, how did the universe really begin? Is the Big Bang truly the final answer? Or could everything we know be only a small part of the truth? Are becoming increasingly urgent. And in this atmosphere, the story of James Webb's latest findings is opening an entirely new chapter. One where everything we thought we understood turns out to be only the beginning of something deeper, more mysterious, and no less shocking. After years of anticipation, the James Webb Space Telescope finally began its operations, and it wasted no time proving its worth with discoveries that were nothing short of revolutionary. Since its launch into orbit in late 2021, James Webb has opened a new window into the distant past of the universe, bringing us closer than ever to the moments right after the Big Bang. Far more than a mere successor to Hubble, James Webb has the ability to see through vast cosmic dust clouds and capture the faint light of the oldest galaxies ever detected. Thanks to its extraordinary sensitivity and expansive field of view, scientists have used James Webb to survey over 30,000 early galaxies, systems that formed only a few 100 million years after the birth of the universe. The shocking part is that instead of finding the small, primitive galaxies predicted by modern cosmological models, astronomers kept encountering massive, well-structured galaxies with far greater mass than expected. Some of these galaxies were as massive, or even more massive, than our own Milky Way, despite existing when the universe had only just emerged from its cosmic dark ages. These results stand in direct contradiction to the traditional model of cosmic evolution, which holds that large galaxies require billions of years to form from small clouds of gas and dust. The early and fully developed appearance of such enormous galaxies poses an unprecedented challenge to current theories of how the universe's structure came into being. And the surprises didn't stop there. Independent research teams expanded their surveys to another 20,000 galaxies, most of them dating from between 500 million and 1 billion years after the Big Bang. Instead of finding evidence that supported the standard lambda CDM model, long considered the foundational framework of modern cosmology, they uncovered even more peculiar galaxies. Some showed clear signs of orderly rotation, directly contradicting the idea that the early universe was dominated solely by chaotic, cosmic debris. Alongside this, researchers identified dazzlingly bright quasars, the telltale signatures of supermassive black holes, appearing unexpectedly just a few 100 million years after the Big Bang. The existence of such enormous black holes so early remains a profound mystery, as current theoretical models cannot explain how they could have formed and grown at such a rapid pace. When all this data was brought together, many of the world's leading scientists were forced to ask themselves, are we facing a major crisis in our understanding of the universe? Could it be that the physical laws we've used to describe the cosmos are valid only within a narrow range, while out there the universe operates according to far deeper and more mysterious rules? That doubt has only grown as more scientists, including some who once strongly defended the Big Bang model, have begun openly voicing concerns that current theories may no longer be sufficient to describe reality. Some have even suggested that we may be standing at the threshold of a scientific revolution, one akin to the moment when Copernicus replaced the geocentric model with the heliocentric view centuries ago. For now, the scientific community continues to watch closely, analyzing every new piece of data James Webb sends back, hoping that the secrets of the universe's origin and true nature will slowly begin to reveal themselves. But as of this moment, one thing is certain. The universe still holds countless mysteries, and the story of how everything began is far from reaching its final chapter. One of the most astonishing recent discoveries made by the James Webb Space Telescope is a massive disk galaxy known as the Big Wheel. The findings were published in Nature Astronomy and quickly drew the attention of the global scientific community. The light from the Big Wheel has traveled for more than 12 billion light-years to reach Earth, meaning that we are seeing it as it was when the universe was only about 1.8 billion years old, just 15% of its current age. What makes the Big Wheel remarkable is not only its staggering distance, but also its complete structure and enormous scale. Detailed observations revealed that the Big Wheel possesses a clearly defined spiral disk, a feature typically associated with mature galaxies such as our Milky Way today. Even more surprising, the Big Wheel is about 3 times larger than other galaxies from the same era and spins at a speed comparable to the largest known spiral galaxies in the modern universe. The existence of the Big Wheel has upended many of cosmology's core assumptions. According to the Standard Model, galaxies in the early universe were expected to be small, lacking in distinct structure, and composed mostly of unstable clouds of gas. To produce an orderly, giant galaxy like the Big Wheel, current theories suggest it would take billions of years of evolution and the gradual accumulation of matter from collisions with smaller galaxies. Yet the Big Wheel tells a very different story, that the early universe was capable of creating massive, complex structures in an incredibly short time. The discovery has also sparked doubt over whether existing galaxy formation models are truly complete. Some scientists propose that for the Big Wheel to have formed so early, it may have originated in an exceptionally dense region of matter, or perhaps involved physical processes in the young universe that have yet to be discovered. Research teams are now analyzing Webb's data in greater depth to study the galaxy's chemical composition and to investigate the possible role of supermassive black holes in its growth. Moreover, the Big Wheel is just one of many large, unusually well-developed early galaxies James Webb has detected in recent months. The sheer number of such galaxies is forcing the scientific community to ask a critical question. Did the universe experience phases of evolution that were far faster and more intense than we've ever imagined? Or are there fundamental physical laws at work that remain completely unknown to us? The discovery of the Big Wheel has prompted research teams around the world to re-examine old theories while working to develop new models that could explain the formation and evolution of the very first galaxies. In the coming years, the James Webb Space Telescope is expected to deliver even more detailed data, discoveries that could continue to rewrite the opening chapters of the universe's history, a story in which every new finding shows that the cosmos consistently exceeds the limits of human imagination. One of the most controversial discoveries in modern cosmology involves a mysterious component that makes up nearly 70% of the universe's total energy: dark energy. Since its discovery in 1998, dark energy has fascinated researchers while also becoming one of their greatest challenges. At first, astronomers noticed something unexpected. Galaxies were moving away from each other at an accelerating rate, contradicting the assumption that gravity should gradually slow this expansion. To explain the phenomenon, they proposed the existence of an invisible repulsive force, which they named dark energy. For more than 2 decades, the prevailing view in science has been that dark energy acts as a constant force, evenly present throughout the universe, driving expansion at a steady rate. But new data from the James Webb Space Telescope is beginning to shake that belief. Recent observations suggest that dark energy might not be as constant as we thought. Instead, it could vary over time or from one region of space to another, making the universe's rate of expansion far more unpredictable and difficult to pin down. Professor Ofer Lahav of University College London and Professor Seshadri Nadathur from the University of Portsmouth are among the leading experts who have publicly expressed surprise at these findings. They argue that the results cannot simply be explained away as measurement error, but instead point to a genuine, previously unknown physical phenomenon. If true, this means our entire understanding of the universe's evolution is being challenged and may need to be rebuilt from the ground up. The situation grows even more complex when scientists confront one of modern cosmology's most troubling paradoxes: the Hubble tension, the inconsistency between different measurements of the universe's expansion rate. When researchers measure using the cosmic microwave background, the faint light left over from just after the Big Bang, they arrive at a relatively low expansion rate. But when they measure more recent galaxies directly or use other methods, they get a much higher number. This difference cannot be explained by simple technical errors. Instead, it hints at a missing piece in our current model of the universe. Some scientists are now going further, suggesting that our very definitions of space, time, dark energy, and cosmic expansion may need to be completely rewritten. Fresh analyses from Webb, combined with data from other major projects like DESI, are forcing cosmologists to expand their thinking and prepare for the possibility that everything we currently know about the cosmos is just one small part of a much bigger picture. With new data continually challenging older cosmic theories, some scientists have put forward bold alternative models to explain phenomena that have so far defied explanation. One of the most intriguing in recent years is timescape cosmology, a daring idea developed by Professor David Wiltshire and colleagues at the University of Canterbury in New Zealand. Unlike the standard model, which depends on dark energy as a mysterious push force, timescape cosmology suggests that the universe's expansion could be the result of differences in how time flows in regions of varying matter density. In this view, the cosmos is not uniform as we usually imagine, but rather a patchwork made up of dense regions, such as galaxy clusters, interwoven with vast empty spaces called cosmic voids. The key to the model lies in the fact that time does not flow at the same rate everywhere. In the nearly empty cosmic voids, where matter density is extremely low, time actually passes much faster than in dense regions filled with galaxies and clusters. Conversely, in matter-rich regions, stronger gravity slows the passage of time. To picture it, imagine 2 perfectly precise atomic clocks, one placed at the center of a galaxy, the other in the depths of a distant empty void where almost no matter exists. According to timescape simulations, after billions of years, the clock in the void could run as much as 1/3 faster than the one in the galaxy. This is not just speculation. It is grounded in well-tested principles of time dilation in gravitational fields, as described by Einstein's theory of general relativity. The implications are profound. The universe may not have a single, fixed age, as we have always thought. Instead, its age could vary depending on where you measure it. Voids, where time flows more quickly, are effectively older than dense regions where time is slowed. Over billions of years, this difference becomes highly significant. Timescape cosmology not only offers a possible explanation for the Hubble tension, the current inconsistency in expansion rate measurements, but also provides a radically new way of looking at the universe. Instead of relying on the elusive concept of dark energy, it explains cosmic expansion through the natural fragmentation of space and the differing flows of time between regions. It is a perspective that could, if proven correct, fundamentally reshape our understanding of reality itself. If the timescape cosmology model truly reflects the actual nature of the universe, then what we currently interpret as an accelerating expansion may in fact be nothing more than a cosmological illusion, the result of differences in the flow of time across various regions of space. Rather than invoking some mysterious form of dark energy to explain why the universe's expansion appears to be speeding up, Timescape proposes that the phenomenon is caused by variations in the rate at which time passes, faster in cosmic voids and slower in dense regions like galaxy clusters. In other words, when astronomers use light from distant galaxies to calculate the universe's expansion rate, they are effectively combining measurements from regions where time flows at different speeds, quick in vast empty expanses and slower in matter-rich areas. This merging of different time rates creates the illusion that the expansion is accelerating, when in reality it may simply be a byproduct of a universe far more complex than the classical homogeneous model suggests. For this reason, many scientists believe timescape cosmology not only explains the peculiar acceleration, but could also eliminate the need for dark energy altogether, a concept that to date exists only in equations and has never been detected directly through experiment. If the hypothesis proves correct, it would mean that our entire method of determining the age of the universe, describing its evolutionary history, and even locating Earth's position within the grand cosmic picture would have to be reconsidered from the ground up. To put the model to the test, astronomers at the University of Canterbury in New Zealand conducted an observational data analysis in 2017. Their results showed that when timescape cosmology was applied to real measurements of galaxy distribution and motion, the model not only fit the data, but in some cases actually explained it better than the lambda CDM model, the long-standing standard of modern cosmology. These findings, while not yet sufficient to overturn existing theories, have ignited lively debate in the scientific community. Some experts argue that if timescape is validated by future observations, humanity could be on the brink of a conceptual revolution in our understanding of time and space, a shift comparable to the way Einstein's theory of relativity transformed our view of the universe in the 20th century. Alongside the mysteries surrounding the universe's expansion rate and the true nature of time, astronomers have recently uncovered another strange phenomenon, one tied to the motion of galaxies themselves. In a large-scale survey, scientists analyzed data from over 30,000 ancient galaxies recorded by James Webb and other major telescopes. The results were unexpected. The majority of these galaxies were rotating in the same general direction rather than being randomly oriented as predicted by the traditional Big Bang model. According to the prevailing theory, the post-Big Bang universe should have been an extremely chaotic environment, lacking any clear order. Galaxies were thought to form from scattered clouds of matter, shaped by gravitational forces and collisions, resulting in each galaxy having its own unique rotational direction. But the survey's findings revealed the opposite, a remarkable uniformity in the spin of galaxies, so prevalent that scientists could not ignore the question of its deeper origin. Some researchers have hypothesized that from the very beginning, the universe may have carried with it a cosmic spin, a large-scale rotation encompassing all matter, space, and time. If this is correct, then the entire universe has borne the imprint of that primordial rotation from the moment of its birth until today. The consistent alignment of galactic spins would no longer be a surprise, but rather an inevitable consequence of cosmic history. Other proposals go even further. Some theoretical physicists suggest that our universe might have been born inside a massive rotating black hole. This idea, known as the black hole universe hypothesis, was once considered fringe, but is now gaining renewed attention in light of these new observations. Under this model, all the space, time, and matter in our universe are essentially the contents of a black hole in a larger parent universe, and the rotation of that black hole could be responsible for the uniform spin seen in so many galaxies. Of course, such theories will require far more precise measurements and extensive future observations before they can be confirmed. Nevertheless, the discovery of this unusual galactic spin alignment has injected new energy into astrophysics, forcing scientists to broaden their perspective and prepare to embrace ideas well beyond the boundaries of tradition. What was once considered standard is now open to revision as each new cosmic discovery leads to more questions, pushing science closer to unraveling the greatest mysteries about the origin and fate of our universe. Looking back at all the findings discussed here, from massive galaxies forming far too early to the puzzling behavior of dark energy, and now to the mysterious coherence in the spin of tens of thousands of galaxies, one truth becomes increasingly clear. The universe still holds countless secrets far beyond our current understanding. Every time scientists believe they are closing in on the truth, the cosmos opens another door, revealing deeper questions and even greater mysteries. The latest discoveries from the James Webb Space Telescope do more than challenge decades-old physical theories. They remind us of the humility and persistence required in the search for truth. Perhaps every model and hypothesis we have today is merely the first step on a much longer journey toward discovering the real origin and destiny of the cosmos. What matters most is that we continue to nurture curiosity, dare to ask questions, and never stop pushing the boundaries of knowledge. If you too are amazed and captivated by these mysteries, share your thoughts in the comments below. What do you think will be the next great question science needs to answer? Do you have your own theory about the universe's unresolved enigmas? We'd love to hear your ideas. Thank you for watching until the very end. Have a wonderful day, and we hope to see you again in the next video.